Okay, so let's talk about what sound is. We're really going to cover three main things in this module. We're going to talk about really what sound is at its core element. We're going to talk about one of the tools that we use to convert the sound into other formats. And we're going to talk about the really basic building block of musical sound. So, first and foremost, sound is a vibration. And it's something like this. On the screen, we have a piano where you hit a key and a hammer hits a string and it makes the string vibrate. And then that starts a chain reaction of molecules moving through the air. We have a microphone which captures that sound and sends it electrically into a computer. It's converted into digital signal, which then can be converted back to electrical and then back into acoustic energy, which then our ear hears, and there's a whole different chemical process after that. So the things that we hear are constantly changing format. But first and foremost, that vibration series in the air, that original sound, that isn't something that moves through the air, it's something that starts a chain reaction. And those little molecules are bumping into each other. And the higher or louder, it's going to do more of an energy displacement. Things that are soft or low are going to do less in different ways. But none of those move. So if I talk to you and we're in the same room, maybe 5 feet away from each other, the air in my lungs is not going to be what goes into your ear. It's going to be a series of movements through the air. The energy will go to your ear, but not the actual air itself. That's just a series of things that bumps off each other. If you can smell someone's breath, it means you're very close to them, and that's a different process of the air from someone's lungs actually being pushed far enough to your nose. That's not the same process. Sound is a different process. But each of these things, then, is what we call a transducer. So that's one of the important terms to know up front. Transducer is something that converts energy from one form to another. So a piano, that's part of it is a type of transducer. Converts mechanical energy into acoustic energy. The hammers that are attached to the keys, they hit the string, that's a mechanical motion. The strings vibrate, and that starts the acoustic energy. The microphone, that captures that acoustic energy. There's a series of magnets inside, which then creates an electrical signal. That then goes into the computer. There's a whole process which converts it from electrical energy into digital. But then the speakers, those convert the electrical output into an acoustic sound and then to our ears. And our ears are able to help convert the acoustic energy into an energy that our brain can understand. So each of these are important, but that really the concept of transducer is really important as we begin the discussion of sound because we deal with them so often in the music business. But let's talk more about sound for a moment. One of the key concepts is that there is a rate of motion that sound is able to do. Now, we talk about this a lot of times in audio as meters per second, but we're going to relate this more into feet because that's the system we use more often in the United States. And a direct conversion would be 1,125.33 feet per second. We are going to simplify this because I do want to make it slightly easier for anything that we do with tests or quizzes or any kind of conversation. We can just say 1130 or 1,130 feet per second. And sometimes sound will move at that rate because it's not a fixed rate. It's not like the speed of light, but it depends on a lot of environmental factors. What's the temperature? What type of things are in the air? Are there any gases that may be different than the normal composition? So it does change depending on a lot of environmental factors. However, because we can't test for those in every situation, at least not with the skills and the equipment that we're going to be using, we can just assume that 1130 is going to be a decent average speed, and that's in average room conditions. What does this mean? So I have the picture here with the lightning and the thunder. And at least when I was a kid, we would always say, once you see the lightning, count seconds. And for every 5 seconds you count, it's 1 mile away. And that's approximately true. And we can actually get there using this math. Even though we start with feet per second, I think that that's more applicable to what we do in the music business because we are sitting feet away from our speakers, not miles. So we wouldn't do how many miles per second it is or miles per hour. But we can use this to relate it to the speed of miles per hour. So for instance, if we wanted to figure this out, what we would do is take what we do know, the 1130 feet per second. So if we want to get this to miles, what we're going to do is, first of all, adjust this into miles. So we would do 1130 times 60, because there's 60 seconds inside a minute. And we would take that answer and multiply that again by 60 to get hours. So if you have a calculator, that becomes pretty easy to do. The first one would be 67,800 times 60 again would be 4,068,000, like that. So that is essentially how far it would go in an hour. That is feet. So now we divide that number by how many feet are in a mile? 5,280, one of the easiest numbers to remember here in Denver. And we get right around 770 miles per hour. So this is an example of some of the basic math we do in the audio industry. Basic algebra, but it's not too complicated, hopefully. Hopefully that's the type of math that you all recognize, even with my messy handwriting here. What we have then is the ability to get a sense for how fast that is. Now, because 770 miles per hour, that is a little bit of how we figure out how long it takes to get to us when we do the lightning example. But where this really comes in useful is when we start talking about musical sound. So what we have with musical sound, say we have a tone, something that's a repetitive sound. You can either whistle or hum or play a synthesizer or a violin, anything. Well, we have our repetitions of the sound, and the rate at which it repeats are what causes that tone. So first of all, sounds are vibrations. Vibrations that happen in patterns create tone. Faster vibrations equal higher pitches. Lower rates of vibration equal lower pitches. And that frequency of repeating, that cycle that happens every second, we call that hertz. Or we do sometimes just say the frequency, but that is the repetition that happens in a second. So on the side here, you can see a keyboard with this frequency information written down. Right here, let's see, right here, I'm going to change the color here to 440. This 440, that is the tuning note of an orchestra. If you've played in an orchestra or band, someone may say, okay, everyone, let's do A440. That is the actual note. And that note, 440 cycles per second, that's talking about, this is 1 second. Then we have a frequency. This is going to happen 440 times each second. That means that when you have molecules in the air, they're going to bump into each other back and forth at a rate of 440 times a second. There's a lot of movement happening that we aren't even aware of. We can't see it. And it's not moving even though it's moving quite fast, we're talking 770 miles per hour. These are very small things and they're not going very far, and the energy is different than if you, say, got hit by a baseball that was going 700 miles per hour. But that rate there becomes really important. Part of this is really hard to conceptualize at the beginning, and so we want to look at this in a little different way. We have that rate of 1,130 feet per second. So, if we think about this in a different way, let's actually simplify this quite a bit. Instead of the 440, which is that A note that we tune with, let's do a 1 hertz tone. So 1 hertz tone, 1 cycle per second. This is low enough that it's beyond the range of hearing. We can't actually hear something this low, but it's a really good example to start with. So this is 1 second. That means our tone is going to fill the whole second. How long is this tone? If we could get enough energy to play a 1 hertz tone, and so we had a big enough speaker that could handle this, with enough power to do so, how long would it take for this tone from the minute it started to the minute 1 second finished? How long physically would that be? It would be 1,130 feet long. So that's a really huge thing. Now, we do say in audio, we say it's pretty typical that equipment should be 20 hertz to 20,000 hertz. That's our professional expectation for quality performance in a studio. That's also approximately the range of hearing. Not everyone can hear down this low, and some people can hear higher than this. It's not a fixed thing, but it's a range of professional audio equipment. So the lowest one that we have would be 20 hertz. Take a second, pause this video, and figure out how long physically a 20 hertz tone would be, or how long it would go in 1 second. Okay, now that you've unpaused the video, let me explain how to figure this out. So, we want to do 20 hertz. That's 20 times per second. So that means all we have to do is 1130 divided by 20. Right? So we have 20 times per second. Sound goes that far in 1 second. That means all we have to do is divide that by 20, and that'll tell us how long each individual part of that is. So if we do that math, we are looking at 56.5 feet. Still pretty long, considering most studio control rooms aren't even that big. But let's look now at the A440. So that note, 1130 divided by 440, 2.5 feet. So it takes about 2.5 feet away from the instrument that's doing that tuning note for that sound to fully develop. Okay, that really is interesting in the context of sound because it tells us that different sounds, different pitches, different frequency ranges are physically different in terms of the space that they need to develop, and also that they're going to be huge in the low frequencies and very small in the high frequencies. So it's really common that we'll have instruments or parts of our frequency range that are up to even above 1,000 hertz, because we go up to 20,000. Once we get past a certain number, it's more harmonics or other parts of the color of the sound, but not the fundamental parts. But even with just 1,000, we are looking at 1 inch. So it goes down from there as we get higher and higher and higher. So now we've looked at a little bit about sound, how it's a vibration. We've talked briefly about transducers and how they're the thing that converts it from one energy form to another. We'll spend more time on those in the microphone section and the speakers. Now we've also looked at the fundamental building blocks of musical sound, the cycles per second or frequency or hertz, and we've looked at how you can figure out the physical wavelength of the musical sounds based on the average speed of sound.